Welcome to the video lesson for grade 12 chemistry on balancing redox reactions. We can start our lesson off with a bit of review. We know that electrochemistry deals with the interconversion between electrical energy and chemical energy, and this is achieved through the movement of electrons in redox reactions, where redox stands for reduction and oxidation. Defining reduction and oxidation, a substance is oxidized when it loses electrons, whereas a substance is reduced when it gains electrons. Right? This allows us to transfer electrons from one substance to the other by gaining and losing. We have a memory aid that helps us remember which of the two is which, where Leo the lion says GER, where Leo stands for lose electrons oxidation, and gain electrons reduction for GER. So we can look at a very simple example of a redox reaction. It's the single displacement of magnesium metal and copper 2 chloride, producing copper metal and magnesium 2 chloride. Now, written as it is, this is what we call the reaction equation, where we're looking at all of the compounds and elements that are involved. But we know that when copper 2 chloride is aqueous and magnesium 2 chloride is aqueous, that they don't exist as lattices where the ions are actually bound together, but actually as dissociated ions in solution. So we could rewrite this to represent that situation where magnesium solid, which is not dissolved, is still just written as is, but the copper 2 chloride, which is aqueous, we can write as copper 2 plus ions in solution and 2 chloride minus ions in solution. And then the same thing on the product side. Copper metal is still written as a solid, it's not dissolved, but magnesium 2 chloride, which is dissolved, can be written as magnesium 2 plus ions and 2 chloride minus ions. And this is what we call the total ionic equation because it shows all of the ions that are present when we do this reaction. Now, if we examine this reaction total ionic equation carefully, we'll see that the 2 chloride ions are present both on the reactant side and on the product side. Right? We call those types of ions spectator ions because they're not really involved in the reaction. They're present both at the beginning and at the end. Nothing's changed about them, so they haven't actually done anything in the reaction. And so when we have spectator ions like that, what we can do is we can cancel them out because they're not really doing anything. And we can rewrite our equation showing only the things that are actually involved in the reaction, which in this case are magnesium and copper. And we call this the net ionic equation because it only shows the things that are actually involved in the reaction. Now we can examine our net ionic equation and we can look at the oxidation states. We know that magnesium, being a pure element, like all other pure elements, will have a oxidation state of 0. Copper 2 plus, it's easy to determine its oxidation state because it's the same as the charge on the ion. It's 2 plus. And then when we look at our products, before looking at our products, we can see that we're going to transfer 2 electrons from magnesium to copper. Right? So our reduction and oxidation are happening at the same time, and the electrons are being transferred from one species to the other. The result of this is that the copper, which was 2 plus, gains 2 electrons and is now copper 0 and becomes a pure elemental form of copper, is copper metal. And the magnesium, having gone from 0 to 2 plus, has lost 2 electrons. Right? And so we know that copper has been reduced because going from 2 plus to 0, it's gained 2 electrons, so that's our GER, gain electrons reductions. And we know that magnesium has been oxidized because going from magnesium 0 to magnesium 2 plus, it's lost electrons, and so that's oxidation. Now we can also look at this in terms of what's doing the oxidizing and what's doing the reducing. We know that magnesium is the reducing agent because it's the thing that reduced copper. It gave electrons to copper and reduced it. Right? And we know that, likewise, copper then is the oxidizing agent because it's the thing that oxidized magnesium. It took electrons away from magnesium, so it's the oxidizing agent. So the thing that gets reduced is also the oxidizing agent, and the thing that gets oxidized is also the reducing agent. So now we can move on to doing something new with our net ionic equation, and that's separate it into what we call half reactions. What we're going to do is examine the net ionic equation in terms of oxidation and reduction separately. Right? So if we look at just the copper, we can see that copper 2 plus going to copper 0 is being reduced. So this is what we would call a reduction half reaction, where we're just looking at the reduction part. And then if we look at magnesium individually, magnesium 0 going to magnesium 2 plus is losing electrons, so that would be our oxidation half reaction. So now we're just looking at the oxidation part. Right? And then the reduction and oxidation parts put together become our total redox reaction. Now we can balance half reactions on their own, much in the same ways you'd balance any other reaction. The first thing you do is look at the number of atoms present. Here it's quite easy. There's only one copper atom present on both sides, and so our copper atoms are already balanced. But with half reactions, there's another aspect that we have to look at. Not only do we have to balance the number of atoms, but we also have to make sure that we have a conservation of charge as well. So we look at the charges on both sides, and we see that we have a 2 plus charge on one side and a 0 charge on the other, which means that our charges are not balanced. The way that we balance charges is by adding electrons to the half reaction. We can balance out a 2 plus charge by adding 2 electrons. So this gives us a complete reduction half reaction where copper 2 plus gains 2 electrons and produces copper 0, and now we have a 0 charge on both sides, or at least a net 0 charge on both sides. We can do the same thing with our oxidation half reaction. We first look at the atoms. We see that we have one atom of magnesium each, so they're balanced. But then we also look at the charges. And again, the charges don't balance, so we're going to balance out the charges by adding electrons. In this case, the electrons get added to the product side, so that now again we have a net 0 charge on both sides. So the charges balance, 0 and 0. And we can see that magnesium solid will produce magnesium 2 plus by losing 2 electrons. Now if we then add our two half reactions together, we'll see that we've transferred 2 electrons in both cases. And so we have 2 electrons on both sides of our added reaction equation. So much like our spectator ions, we can cancel out the 2 electrons that appear on both sides, and we're left with a balanced net redox reaction. Right? Now, because this is a very simple single displacement reaction, it's actually very simple to balance. But the whole reason we went through this process of half reactions is that sometimes you get more difficult redox reactions to deal with, such as this one where we have iron 2 plus reacting with dichromate to form iron 3 plus and chromium 3 plus. This one may not be particularly obvious right off the bat how to balance on its own. So we can take it through the same process. First of all, looking at the oxidation states, we see that iron 2 plus obviously has a 2 plus oxidation state. It's the same as the charge. But with dichromate, it requires a little more work to figure out the oxidation state on chromium. It's not the charge on the overall ion because it's a polyatomic ion. Taking into account that the oxygens will all be 2 minus and that the ion as a whole has a 2 minus charge, each of the 2 chromiums must have a 6 plus oxidation state. On the product side, again, it's much simpler. Iron 3 plus has a 3 plus oxidation state, and chromium 3 plus has a 3 plus oxidation state. Usually, provided that oxygen isn't bound to itself or to a more electronegative atom like fluorine, oxygen will always have a 2 minus oxidation state. So when we look at these, we can see that iron is being oxidized. It's losing an electron, and it's going from 2 plus to 3 plus. Whereas chromium, on the other hand, is being reduced. It's going from a 6 plus oxidation state. It must be gaining 3 electrons to get to its 3 plus oxidation state. So we can now separate this into separate half reactions, where we can look at the iron only, and the iron is going from 2 plus to 3 plus, so that'll be our oxidation half reaction. Then we can look at the chromate and chromium, or sorry, dichromate and chromium, and it must be our reduction half reaction. So now what we're going to do is we're going to balance out our half reactions individually. The oxidation half reaction is quite simple because, again, there's only one iron atom on both sides. And then all we have to do is balance the charges. So we have a 2 plus charge on one side, a 3 plus charge on the other. So by adding 1 electron to the product side, we now have a 2 plus charge on both sides. Now, because we're dealing with a polyatomic ion in our reduction half reaction, we're going to have to go through a little more work to get this one balanced. We start off by looking at the chromiums, and we see that we have 2 chromiums on the reactant side. So to balance out our chromium atoms, we need to have 2 chromiums on the reactant side, or on the product side. Now, as I said, we have a polyatomic ion, so to balance our atoms, we also have to consider that we have 7 oxygen atoms, and we have no oxygen atoms on the product side. What we're going to do is we're going to add water in order to balance out our oxygens. Since water contains 1 oxygen atom, we can add 7 water molecules to the product side, and that'll add 7 oxygen atoms. Now, this, of course, causes the issue that we've now added hydrogen as well, so we need to balance our hydrogen atoms now. And we can do this by adding H+. This hydrogen in water has a +1 oxidation state, so we'll add 14 H+ to the reactant side, which will balance out our 14 hydrogen atoms. So we've successfully now balanced all of the atoms in our reduction half reaction, but again, we need to look at charges as well. So if we examine the charges that are present, we can see that we have 14 plus charges from the H plus and 2 minus charges from dichromate. And then we also have 6 plus charges from our 2 chromium 3 plus ions. So totaling all of these up, we have a 12 plus charge net on the reactant side, and we have a 6 plus charge on the product side. So there's far more positive charges on the reactant side, which means we're going to have to add electrons to that side in order to balance out our charges. Since we have 6 extra positive charges on the reactant side, we'll just cancel them out by adding 6 electrons on the reactant side. So now that we've added 6 more negative charges, that changes the net charge on the reactant side to 6 plus, which now causes our charges to balance. We have 6 plus charges on both sides. So notice that the charges don't need to be 0 on both sides, they just need to balance. So now that we've balanced our charges, we have 2 balanced half reactions. The only issue now is that in order to add our 2 half reactions together, we need to make sure that we're transferring the same number of electrons. If we look at the electrons in both half reactions, we find that we only have 1 electron in our oxidation reaction, whereas we have 6 electrons in our reduction reaction. In order to transfer the same number of electrons in our oxidation and reduction, we're going to have to multiply our first reaction by 6. This will give us 6 electrons in the oxidation reaction, so we'll be transferring 6 electrons back and forth. Now we're in a position where we can add our 2 half reactions together. Remembering that we multiply the first reaction by 6, our reactants are going to be 6 iron 2 plus from the oxidation, and then 6 electrons, 14 H plus, and 1 dichromate from the reduction. And then this will produce in our products 6 iron 3 plus and 6 electrons from the oxidation, and then 2 chromium 3 plus and 7 waters from the reduction. If we've done this correctly, we should notice that we have equal numbers of electrons on both sides of the reaction. This also means that we can cancel out the electrons on both sides of the reaction. And we can rewrite our reaction equation, now just showing the irons, the chromiums, the H plus, and the water. And what we've done now is we've successfully balanced our redox reaction. And because it involves H plus on the reactant side, what we've done is we balanced the reaction for acidic conditions. So this brings us to our next slide. Since we don't always do reactions under the same conditions, right, we can also balance the reaction for basic conditions. It's the same reaction, but if we wanted to do it under basic conditions instead, we're not going to have H plus around. So what we do is we start off with the reaction we just finished, the balanced reaction for acidic conditions. Now what we need to do is we need to neutralize the acid, right? This is how we're going to get basic conditions. In order to neutralize H plus, what we can do is add hydroxide. Hydroxide will neutralize H plus. Now, sort of like mathematical equations, where if you want to make a change to an equation, you have to change both sides, right? We don't actually want to change our reaction equation, right? So in order to have no net change, we need to add 14 hydroxides to both sides of our balanced equation. So after adding 14 hydroxides to both the reactants and the product side of our reaction, we can rewrite our reaction equation, right? Where instead of writing hydroxides and H pluses on the reactant side, we're going to combine the hydroxide and H plus that we put there. And when they neutralize, they form water. So 14 hydroxides and 14 H plus are going to combine to form 14 water molecules. So at this point, we've successfully gotten rid of our H plus, and now because we have 14 hydroxides on the product side, we now have basic conditions. The only thing is that you'll notice we have waters on both sides. So again, like spectators, anything that appears on both sides of our reaction equation we can cancel out. All 7 waters on the product side can be canceled, and 7 of our 14 on the reactant side can be canceled out, leaving us with just 7 left over. Finally, rewriting the reaction again, we now have a balanced reaction for basic conditions. So all the H plus is gone, and we have hydroxide instead. Notice though that the amounts of iron and chromium haven't changed. It's just the waters, hydroxides, and H plus that we've actually altered. So let's try and consolidate this then into a set of steps that we can use in order to balance any redox reaction. Notice that the first thing that we always did was we separated our reaction equation into oxidation and reduction half reactions so that we can balance each of the half reactions individually. The first thing that we balance is our non-oxygen and non-hydrogen atoms in each of the half reactions. Then we move on to balancing the oxygen atoms, and we do this by balancing oxygens out with added water molecules. Now, we'll then need to balance hydrogens, so we can balance hydrogen atoms by adding H+. Once we've added H+, right, we should have balanced all of our atoms, but remember that we need to balance charges as well in our half reactions. So we're going to balance our charges by adding electrons. Once we've added electrons and we've balanced our charges, we need to examine both of our half reactions and make sure that both half reactions contain the same number of electrons. That way, when we have a transfer of electrons, we're transferring the same number of electrons for reduction and oxidation. Once that's taken care of, we can add the two half reactions together. If we've done it correctly, the number of electrons on the reactants and product side should be the same, and we can cancel them out. What we may also find is that there's some other species that we can cancel out on both reactants and product side as well. for example, H plus or water. And once we've canceled anything that appears on both sides of the equation, we now should have a reaction that is balanced for acidic conditions. Now, if you're looking to balance your reaction for acidic conditions, you're now done. You can stop at step 8. But sometimes we need to balance our reaction for basic conditions, and so we may need to go on and do a couple of extra steps, taking our balanced equation in acidic conditions. We can now change it to basic conditions by adding equal amounts of hydroxide on both sides of the equation in order to neutralize any H+. If we combine any H+ and hydroxide that appears on the same side of the equation, they'll neutralize and form water. And then finally, we can go ahead and cancel any water that appears on both sides of the equation. And we should now have a complete balanced equation for basic conditions. So let's see if we can try and take these steps and do a practice. Okay. Take the reaction between dichromate and ethanol to form chromium 3+ and carbon dioxide. Pause your video now and see if you can work this out on your own using the steps that we just developed. Okay, hopefully you're able to work this out on your own, but in case you ran into some trouble, we're going to take it up. So the first step, of course, is to separate our reaction equation into half reactions. So dichromate is, we've seen this half reaction already in the previous example. The dichromate is going to be reduced to chromium 3+. So we need to first balance our chromium atoms. We have 2 on the reactant side. We can list our second half reaction first. If the chromium is being reduced, then the ethanol is being oxidized. It's the carbons that are being oxidized here, if we look at the oxidation states. Yeah. Then we can balance our chromium atoms. So we have 2 and 2. Right? Then we need to balance our oxygen atoms, and we're going to do that with water. So we have 7 oxygen atoms, so we add 7 water molecules. And then we want to balance our hydrogens with H+. So we have 14 hydrogen atoms, so we need to add 14 H+. Now that the atoms are balanced in our first half reaction, we need to balance the charges, right? And we'll find that we need to add 6 electrons to the reactant side so that we have a net charge of 6+ on both sides. So now that we've done that, we can move on to our second half reaction, and we'll go through the same process. Right? We first want to balance our non-oxygen and non-hydrogen atoms, so that would be carbon. We need 2 carbons on the product side. Now that our carbons are balanced, we can balance waters and oxygens. So on the product side, we have 4 oxygen atoms, so we need to add 3 waters so that we have 4 oxygen atoms on our reactant side. And then the next step would be to balance hydrogen atoms. So we need to add 12 H+ to our product side so that we have 12 hydrogen atoms on both sides. And then lastly, we want to balance charges. We see that we have no charge on the reactant side, and we have a 12+ charge on the product side. So to balance that out, we add 12 electrons, so that now we have no net charge on both sides. Now that we've balanced each half reaction, we need to make sure that we're transferring the same number of electrons. So we'll see that we have 6 electrons in our first half reaction, whereas we have 12 electrons in our second half reaction. To make sure that we're transferring the equal number of electrons, we need to multiply the first reaction by 2. So now we have 12 electrons in both. And now we're in a position to add them together. When we do that, we get this complete reaction equation. And we now need to start looking for things that appear on both sides of the reaction. We know that if we did this correctly, we should have the same number of electrons on both sides. So we can cancel out our 12 electrons on both sides. But we can also look for other things. We'll see that there are 12H plus that can be canceled out. If we cancel 12H plus on the reactant side, we're left with 16. And then we can also see that there are water molecules on both sides. So if we cancel 3 waters, we'll be left with 11 waters on the product side. So now that we've canceled everything out, we can rewrite our equation. And what we get is 16H plus reacts with 2 dichromates and 1 ethanol to form 4 chromium 3 plus, 11 waters, and 2 carbon dioxides. And that's our final reaction equation balanced for acidic conditions. Now there's one last thing to look at, and it's an interesting type of redox reaction. It's called disproportionation, right? And what that means is that one element is going to be both oxidized and reduced. So we're oxidizing and reducing the same element, right? So I can give you an example of what that might look like. Here, chlorine, just pure elemental chlorine, right, can form chloride and hypochlorite, right? Cl minus and ClO minus, right? And what we can see is that we only have one element on the reactant side, that's chlorine, right? And if we look at the oxidation states, since it's elemental chlorine, it's bonded to itself, both of those chlorines have a 0 oxidation state. But on the product side, one of our chlorines has a -1 oxidation state, whereas in hypochlorite, the chlorine has a +1 oxidation state because the oxygen is 2 minus. So we can see that our chlorine has gone from 0 to -1, which is a reduction. It's a gain of electrons. But it's also gone from 0 to +1, which is a loss of electrons and therefore an oxidation. So we can actually deal with this in the exact same way that we've done the other reactions. We separate it into 2 half reactions, right? One for oxidation, one for reduction. So our reduction half reaction looks like this. It's chlorine reacting to form chloride. So that's a gain of electrons, it's reduction, right? And then our oxidation half reaction is going to be chlorine going to hypochlorite, which is a loss of electrons, so that's an oxidation, right? So notice that chlorine appears in both of our half reactions. So now we go about balancing them in the exact same way that we did everything else. We're going to balance atoms first. So we need 2 chlorine atoms in the first reaction. We don't have any oxygens, so we don't need any waters. We don't have any hydrogens, so we don't need any H+, right? But we do need to make sure that the charges are balanced. So since we have 2 chloride minus on one side, we need 2 electrons on the reactant side so that we have a 2 minus charge on both sides of the reaction. And we can do the same thing with oxidation. We need to balance our chlorines first. This time we do have oxygens. So since we have 2 oxygen atoms, we need 2 waters. And now that we have 4 hydrogen atoms, we need 4H+. And now we need to balance our charges. So we have a neutral side on the reactant side, and we have 2 plus on the product side. So we need to add 2 electrons to the product side, and now we have a net neutral charge on both sides. Now we check to make sure that we have the same number of electrons being transferred, and we do. In both half reactions, we're transferring 2 electrons. So now we can add our 2 half reactions together. Since we've done this correctly, our electrons cancel. Now we can rewrite our reaction equation where we've combined chlorine and chlorine. Right? We have 2 chlorines on the reactant side, so we just combine that to 2 chlorines. Right? And if we look at all of our coefficients, we notice that they're all even. So if we want to, we can actually reduce all of our coefficients by half. And we can rewrite the reaction equation with new coefficients. And this is our final balanced reaction equation for the disproportionation of chlorine in acidic conditions. So this is actually what happens when you bubble chlorine gas into water, right? You will produce chloride ions and hypochlorite ions along with some acid. So this will produce an acidic solution. And This is actually one of the processes for making bleach, which is sodium hypochlorite solution, by bubbling chlorine through water. If you neutralize the solution, the acidic solution afterwards, you'll end up with sodium hypochlorite and a bleach solution. So I think that covers pretty much everything we need to know in order to balance redox reactions. So thanks for listening and enjoy your practice in class.